now we'll talk about Spark. So how many of you know what is a big data? Yeah, so 50% of people came to eat pizza. Okay. That's good, actually. Anyways, so if you were a management consultant, you would say that big data is defined by 5 V's, which I always forget. Volume, velocity, veracity, variety, and value. So yeah, I'll skip the 3 last V's, but the most important ones technically are volume and velocity. And so typically when we talk about volume, it's tens of terabytes or petabytes of data. And we typically do batch computations on this data, and they have to run on, like, let's say, tens or hundreds of computing nodes, typically a general purpose hardware. If we talk about velocity or streaming computations, we are talking about, let's say, hundreds of thousands or millions of messages per second per node. And let's say latency, 1 second, 100 milliseconds. And again, scales up to, let's say, 100 computers. And I guess the first question you have to ask yourself, do you actually have big data? So in many cases, if your data fits into one very large computer, which might have a terabyte of memory and 100 cores, then maybe you shouldn't use big data technologies. And maybe you use Python, because actually most of Python is written, well, the core of Python is written in C++, all machine learning things are in C++, and Python is just a small wrapper around it. So think about it. There's also lots of specialized systems for different kinds of hardware or different kinds of use cases. So for instance, TensorFlow is one example of which Chris will talk more later. All right, so who knows what is a Hadoop? Okay, 25%. So Hadoop was modeled around some papers written by Google around 2003. The papers were published, and I think Hadoop was created as a project in 2006. And so a typical stack looked like that. So at the bottom of all these things, there is a zookeeper, which is a coordination layer, which is fault tolerant to keep their metadata, some locks, you can get notifications when things change, and different components use zookeeper to basically exchange information. Then there is a scheduler or resource allocator. In this case, it's Yarn, which allows you to, let's say, book some amount of computing resources for your task. So let's say you say, I want 25 cores, so much RAM, and 5 instances of that. And Yarn will basically give you, if it can. Then there is a file system, HDFS. It's a distributed file system. It was designed to be working on rotating hard drives. So not much random access, but more like sequential access. And typically, the files are written once. They cannot be changed, but they are split into blocks of, let's say, 10 megabytes or 100 megabytes. And each block is kept on one or more computers, so they are replicated. And the important part is that there is a data locality, so when you run your job, when possible, your computations will be shipped to the data, not the other way around. And on top of that, there was implemented a key value store, HBase. Who knows or has used HBase? All right. 0, okay, 1%, 2%. And Cassandra, well, yeah, a bit more. I think it's 10%. Cool. Any other key value stores? MongoDB. All right. For some definition of key value store. Yeah, so HBase basically is a key value store which works on top of HDFS. I will not bore you very much with it because it's not the topic of today. And on top of all this stuff, there is a MapReduce framework, which was well, a standard way of writing distributed computations, which we'll talk later about, using which, for instance, Google's PageRank was implemented, and later many other things. And as the time progressed, around 2010, projects like Spark and Flink were, well, let's say, made public or initiated. And what they did is basically they looked at real production clusters. They looked what is slow, what are the bottlenecks, and they optimized these problems and created, well, different kind of architecture. Also, we have to understand that the hardware changed. So what changed between now and 10 years ago is that the amount of RAM available in computers and clusters has increased by a very large amount. And so originally Hadoop was meant as a system which didn't use too much RAM, but actually was more like, read sequentially from disk, write to disk, send over network, and so on. While things like Spark and Flink, when possible, try to keep things in memory. But if the working set is in memory but something doesn't fit, they still can work with spilling data over to hard disk. But let's say the best speed up is achieved by having enough RAM where the stuff sits there. All right, so now the hipsters in San Francisco are using a SMAC stack. SMAC stack, well, again, it uses Spark, but instead of Yarn scheduler, there is a Mesos, which is kind of alternative version of resource allocation manager. It's more generic, and so on. So, well, in this particular stack, also Akka is advertised. So we have talked about Akka and reactive systems before. Hopefully, people know about it. How many people know about Akka? Okay, so at least not every time only new people come, but also some last times people. So it's not all so bad. And yeah, key values store Cassandra and event streaming Kafka. How many people know what is Kafka? Cool, everybody knows Kafka. That's, by the way, not a writer, it's a different thing. But it's related. There are also queues and bureaucracy. And finally, the pancake stack. So pancake stack is something which Chris is advertising. It's really the idea that there's lots of technologies which are pretty advanced and useful. And I think Chris will tell you more about it if he wants to, and he also has some workshops about it. But like the pancake stack is really just the idea how you can wire them up together. And again, as you can see, there is a Spark there. So yeah. People have interesting sense of humor in San Francisco. So how many of you actually know what is MapReduce? Okay, so I'll just very fast skip over it. So suppose you have a bunch of text data on your HDFS disks. So each file, actually one very long file containing lines of text, which is split into chunks stored on different partitions of your HDFS cluster. And you want to count the number of words in the file altogether. So what you do is basically, first this data is split or has been already split by HDFS into chunks. And first you apply something called a mapping function, which on each chunk, for each line, basically produces a sequence of keys of values. In this case, these are words, and they're counts. So these are keys, these are values. And well, as you can see, well, these are words, and it copies them there. And if some word is repeated many times, well, the counts will be larger, right? So in order to actually count the number of words, so bear in mind that this can be on different computers, a shuffling operation is performed where data with the same key is all aggregated into the same machine. As a result, you will get a sequence of well, entries with the same key and different values. And then a reduce function is applied. In this particular case, this reduce function is adding together these numbers. Yeah, this year, the Spark. Anyways, the result is that yeah. It's Christmas soon. There is Star Wars. So it's like yeah. Anyways, the result is that you, in the end, get the final result with the word counts. And theoretically, you just have to provide two functions, a map function and a reduce function. In practice, there is lots of just craft and overhead. How many people understood this description? Who didn't know about MapReduce before? Yeah. Okay. So the problems of MapReduce. Writing MapReduce jobs is verbose. Like, it's a lot of Java code. Also, Java is verbose. there is a pretty high overhead of starting the jobs. It can be seconds or even tens of seconds. And many real-world computations, such as, for instance, PageRank, are actually iterative. So you run multiple MapReduce jobs in a sequence. And now the problem is that after the end of each MapReduce job, the data gets onto the HDFS. And this means that every time you run one iteration, the data hits the disk instead of staying in memory, even if it were possible. And as a result, well, you have lots of RAM and you're not using it, and you're just, reading and writing on disk stuff. And yes, Hadoop was written in unoptimized Java, which means basically lots of Java objects, and Java objects have huge memory overhead. They are very bad with the CPU caches, if you know how CPUs work and so on. So if you really know how JVM and CPUs work, you can write much more efficient Java code. It's also really hard, so don't try it at home. I only pretend I know how to do it because I don't really. Yeah, so what Spark did was, let's say in the 1.x versions, because actually during this summer they released 2.x version 2.0, which we'll talk about in the end. So their main achievements were productivity. You could, let's say, write your functions or computations maybe in 10 times less lines of code. And you could use, let's say, functional programming approach, like with lambdas, if you know what, hopefully you know what are lambdas. But if you really wanted to, you can also do it in Java. And nicely, you have a REPL, read, eval, print loop, or you can actually try out stuff very efficiently, and you don't have to wait for seconds for the result. And interestingly, actually, the performance was up to 10 times faster when your data fits in RAM, but it was even still faster even if it didn't. So pretty nice result. And now we actually get to talk about Spark. How much time did I waste on intro? 15 minutes. All right. So this is the word count in Spark in two different languages. This is in Scala, and this is in Python. So PySpark is really just a Python wrapper around Spark. It is still less efficient than the Java or Scala-based Spark, but it's getting better. And so we'll talk about the details later, but just appreciate the amount of lines. It's like 5 lines of code. And this is a word count in MapReduce. The sound effect doesn't work anymore. Oh well. Anyways, yeah, it's lots of lines of code. You don't have to read it, but it's pretty scary. And so here are the Spark 1 components. It runs on different schedulers. Yarn Mesos, it has its own scheduler. There is a Spark core, about which we'll talk the most. And there is a bunch of projects running on top of Spark. There's structured data processing using Spark SQL, Sparse Streaming for, well, processing streams, machine learning, and graph processing. So are there any questions so far? All right. So the main concept of Spark is something called resilient distributed datasets, RDDs. How many people know what it is? So basically, very conceptually, RDD is just a collection of values, which is read-only. Actually, sequential collection of values. And you can apply typical things you can apply to a list or a map. In Scala or other functional languages, map, filter, flat map, join, and stuff like that. We'll look at some examples later, but well, that's the idea. And importantly, transformations should not have side effects usually, and they can be re-executed by Spark if Spark decides it might be necessary. Usually it doesn't happen, but it might. And in the end, there are actions which well, do something useful with the data you computed. You can output it to some external systems, or you can, for each entry in your data, to do something with it. And transformations are actually lazy, which means that as long as you're putting together your transformations, nothing actually runs. But once you actually do an action, you actually get something useful, things start happening. And so actually, now let's look at this word count thing in Spark. So there is some kind of Spark context which you first open a file on an HDFS. This is already an RDD of the lines in this file. And then what you do flat map. I'll explain you what this flat map is in case you don't know. By the way, how many people know what's a flat map? Good, good. Well, basically what happens is that you take one line, you split the line into words by the space, and then for each line you get a list of words. But what flat map does is basically it concatenates for each line together these words into one long sequence of words. Then we apply a map function, which for each word replaces it with a word mapped to, well, 1, which is the number of words. And then there is again this reduce function, which, well, essentially adds together for each word the number of ones here. So this is reduced by key. So for each word, you get the, well, basically to aggregate these ones. So very similar to MapReduce, but much, much less lines of code. And in the end, you take these counts and you actually apply the action, save as text file to HDFS, and actually things start happening only once you run this method. Before, it's just, you are putting together your plan, what you want to do. Any questions about this slide? Sorry?
Is it distributed? How this red box distribute?
So your question is whether it's distributed or? Yes. I'll tell you about that.
What's that underscore notation?
Oh, so really it's just a cool Scala syntax. If you're lazy and you don't want to write a comma b mapped to a plus b, you can write underscore plus underscore, and it just says that this is a function with 2 arguments. Please put them here. It also makes Scala unreadable, but don't tell anybody. Yeah. So actually, RDDs are partitioned and potentially across multiple computing nodes. And once you actually start optimizing the jobs, you will have to think about how they are partitioned, and it's possible to tell the key of each partition. And importantly, partitions are expressed as a computation from some other input partitions, and this is called lineage. And altogether, this partition dependency graph forms a DAG, directed acyclic graph. And I'll show you a nice picture, but just remember that these dependencies can be narrow or they can be wide. So here is a nice picture. So here is one RDD. The blue thing is our partitions. And then there is another RDD, which is computed from this RDD. And these are the dependencies. So this is the narrow dependency where each partition is computed from the previous partition. And the nice thing is that if Spark wants, it can actually do it on one machine. It doesn't have to move data between the machines, but actually it can put these 2 stages together. It's called pipelining. Well, the same thing happens here, right? So there is a narrow partitions. And now we want to join these partitions, which is, well, similar to reduce. And for that to happen, the partitions have to be, RDDs have to be partitioned on the same, well, key. The way it's achieved is by doing a shuffle where data, which, well, basically you want to take data from different parts of different partitions and move it, the relevant data to this partition, relevant data to this partition, and so on. And so once you have 2 RDDs co-partitions, so they're partitioned on the same key, the join process becomes trivial because, well, there is, you don't have to shuffle data around. I hope somebody understood what I just said. How much time do I have? All right. So then I will tell you more about partitions. So in the end, this directed acyclic graph of RDDs is compiled into an execution plan. And generally, partitions are kept in memory. But if there is not enough memory, they will be spilled to disk. Also, if some partition is lost, for instance, when a node dies, Spark can recompute it on another node because they don't have side effects, so they can be always recomputed. And also, if some partition computation becomes slow, Spark can speculatively run the same partition on another computer and just see which one finishes first. Once the partition has been used by the next partitions in the dependency graph, the partitions can be released. And finally, if you want to keep the partitions around, you can mark them as cached or persistent. And in this case, the RDD you have marked as persistent will stay around, for duration of something called Spark context. So this way you can reuse data if you feel it's necessary for you. Otherwise, it will go away once the job finishes. And so here is actually a nice picture that of the pipelining. So what will happen is that, because there is a narrow dependency, these two partitions will be computed by one task without any kind of moving data around. And there is also a potential for writing a code which really just does two things immediately. Like not two loops which somehow interact with each other, but really just fuse them. Yeah, so lots of smart things happen behind. Hopefully you don't have to always think about them, but probably sometimes when you need to do some performance optimizations. Any questions about this stuff? Cool. All right. So Sparse Streaming is this streaming framework built on top of Spark Core. And how it works is that you describe your streaming computations in a syntax which is not identical to Spark Core, but very similar. And Spark Streaming will basically translate it into computations using RDDs and usual Spark operators. And so Spark Streaming can process event streams from different sources like Kafka, ZeroMQ, TCP, and so on. And it can also output data to various data sinks. Well, I have listed them on the screen. I will not read it out to you. It's a long line. And the important thing is that it's very developer productive to prototype things because the syntax is very similar to the regular Spark core. However, the truth is, like, writing a prototype is easy. Getting it to work efficiently and scalably is a whole different story. So maybe actually Chris can comment on this one. I was ranting about the fact that Spark Streaming is easy to prototype but hard to get into production.
Yeah.
Can you give us an update? Maybe it's better now.
Some pretty strong opinions about Spark Streaming. Does anyone use Spark Streaming right now in production? What version of Spark are you on?
The latest one, 2.01.
Oh, are you? Okay.
He's running.
Yeah, I mean, I can talk about it later, but yeah, Spark Streaming, it's difficult to reason through some of the cases. What's the source that you're using?
We're using RabbitMQ.
Okay. Yeah. Yeah, I mean, like whenever you do Spark Streaming, you want a source that can buffer, because always assume Spark Streaming is going to be down. So just as long as you can buffer on the source, and then also the ability to replay, which I'm going to talk about that in the context of data science, being able to replay like messages coming in, and then you can train and sort of. So, yeah, Spark Streaming, it's difficult to reason through sometimes. The state, like managing some of the state. Do you maintain stateful operations right now or stateful data?
Hello.
Yeah, that's sort of a long story.
Yeah, my recommendation is to always get shit out of Spark Streaming as quickly as possible.
it because like most people don't really have a true like real-time need. You know, you ask around and it, like ends up being 15 minutes or yeah. One customer I was at, I somehow negotiated them down to 4 hours for being there like real time. So yeah, that
Cool.
saved a lot.
So I might also say blasphemy, but if you have a queue and a database, you can write a piece of code which reads from queue and updates database with transactions. And if it works for you, then, well, you don't need sparse streaming. But there are cases probably when it is needed. Anyways, so there is a way to achieve reliability against crashes. And the way it's done is that Spark is snapshotting the RDDs on the HDFS. So even if you restart the whole thing, it can continue from some safe state, at least in theory, and it's getting better in practice. It also now have a back pressure, which means that it will not get overloaded by data, and it can actually adjust the size of its buffers. And it uses PID controllers, if somebody knows what it is. Yeah, and so it has pretty nice throughput, and it's probably its biggest advantages. Its kind of design trade-off is that it's a micro-batching system, which means that it takes a batch of data from a data stream, let's say worth of 1 second, and then does something with it and then outputs it. So getting it to probably 100 milliseconds is pretty hard. So you will be like dealing with 500 milliseconds latency usually, I guess. So here is a word count example in Sparse Streaming. And well, what you do here is really you create this streaming context, micro batch duration 1 second. You get the lines of text from a socket stream. And then hopefully this code is very familiar to you because it's exactly the same we had before. The types are different because these are not RDDs, these are D streams. But the syntax is pretty much identical. And in the end, it can print stuff out. All right, and so I have this nice picture which I took from the Spark tutorial. I hope they will forgive me. So this is this D stream. So on the previous slide, these lines, words, pairs, and word counts, these are all D streams. And so one D stream is basically at each micro batch. It's a representation of, let's say in the beginning, it's a representation of data you took from your data source, like Kafka. So here is the data from the first micro batch, here is the data from the second micro batch, and so on. And then you do some operations on it, and you get another D stream, which, well, for instance, has this information about words. So like flat map operation and so on. Though that's how Sparse Streaming works. Can somebody tell me, first, if there are any questions?
Why is it called words D stream? Because the words is
Sorry?
Is the actual mapping? It's like the second layer.
So it's a D stream, it's because it's a discretized stream. So the idea is that every time you apply some kind of transformation, you had a D stream and you get another D stream, which is also like a sequence. Well, any kind of transformation, right? So like the ones we had with RDDs before, like there's a long list of them. Any other questions? So I kind of cheated on you. Does anybody have an idea how? Well, I mean, I didn't have any state here, so there is no state moving between time steps. So for real, you should have another sequence of RDDs which actually depend in that direction, because otherwise, for each micro batch, you will just get the counts of words in this micro batch, but there is no cumulative counts of words, which makes it for a really boring streaming application. So there is this magic function called UpdateStateByKey. And so what it does is that we had these word counts, right, for each micro batch. So this is not cumulative. And then we applied the function UpdateStateByKey, which, well, we apply update function. This is the place where Scala gets ugly, just ignore it. But otherwise, Scala is a really nice language. So this update function basically will do, so the key is a word, and what it gets is a bunch of essentially counts from the last microbatch for this word. And it will also give you the previous state, which is this running count, essentially. And at the first microbatch, it will be none, because there is no running count yet. And later, it will be, well, whatever you accumulated so far. And so, well, what you do here, you add them together, and you, well, take this one or a 0 if it's a none, and you return the new count. And using this magic operation, you will get stateful RDDs. So what will happen is that there will be another layer of RDDs here, corresponding to each microbatch epoch, or whatever is the right name. But the dependencies will go in that direction, and things actually get more interesting. So the thing is that they later realized that this function is not the most optimal for doing the API for streaming. And now there is another function, if I'm not mistaken, called MapWithState. It allows easier to extract some kind of delta information from how your state changed from the last state. So just look into it if you are optimizing your streaming jobs. But yeah, so that's the idea. And I think it's pretty cool. Did anybody understand? 50%? No, that's good. 50% of people, 50% of content.
How would count these RGBs at the end if you want to get like flush into the one answer? So you need to another stream and then...
And the last RDD will be the cumulative. Yeah, yeah. And obviously you can build much more complicated computation graphs. And so, like, conceptually you can think that you have a SQL, right? A SQL can be translated into a bunch of filters, aggregations, maps, joins, and so on. And you basically get a streaming SQL if you want to. So there are other frameworks which have different trade-offs. So like I said, the Sparse Streaming definitely trade-offs for high throughput, but it also has pretty high latency, like second or half a second. We are in the European Union, and there is another fantastic framework called Flink, which by their own claim at least has much lower latency because they have essentially their core framework is built on streaming, so they don't have their smallest unit of work is much smaller, and as a result, at least they claim the latency of their streaming jobs is much lower than for Sparse Streaming. So be patriotic and check it out. It's actually pretty good. Any more questions about Sparse Streaming? So another thing is called Spark SQL. So what Spark SQL allows you to do is to run analytical SQL queries on various external data sources, which are hidden behind the standardized data source API. Well, there is a bunch of different data sources. I will not read them to you. And importantly, it can do predicate pushdown. How many people know what's a predicate pushdown? All right. So basically, when you write a SQL, and there is some where condition, like age less than 5, when accessing the external table, instead of doing a full scan of a table, you can pass this condition immediately to the external source. Because the SQL itself in the Spark, it will be executed inside of, well, Spark, right? So it will translate SQL into a bunch of RDDs which do something. But they first have to pull data out from external sources, and the less you read from there, well, the nicer. And so what happens is that if it's possible, the where conditions will be passed to the external data sources, and you will get the filter data. So how many people know now what's a filter pushdown? Okay, good. So yeah, pretty obvious example, also pretty boring example. So you basically open some kind of JSON table. It will, I think, infer the schema automatically. Then you register it as a temporary table people, and then you can actually run SQL on it. And interestingly, there is actually also, let's say, well-typed domain-specific language called DataFrames, which you can express the same SQL but using the Scala API. So you can do the same things like filter, select some attributes, joins, and so on. And well, as opposed to SQL, it will be actually checked compile time. Any questions about Spark SQL?
Does it use indexes or it just runs sequential scan on these weather conditions?
So the thing is that for external data sources, right, it will try to push the filters outside, right? And if this external data source has an index, then it will be applied. However, if we have time, I will show you some slides about columnar representation. Like typical columnar databases don't really have indexes in the regular sense of the word. So they have very efficiently represented columns of data, and you still can pass it a filter, but instead of looking into index, it will just scan extremely fast the data and bet that by the fact that it uses CPU caches extremely efficiently, and most programs use it horribly, it can do it faster than with indexes because it also doesn't have to jump around the hard disk, because the indexes usually will tell you go there and go there and go there, as opposed to just scanning through very fast. So there is a trade-off. So definitely this is OLAP, this is not OLTP, right? So this is analytical processing, not transactional processing. Any more questions? So DataFrames API. So actually the rest of my presentation will probably have a word DataFrame on each slide. But the idea is that DataFrame is something which they want now to put at the core of everything. And it's a type DSL, which has a functionality which is at least as powerful as SQL, but it can have more operators if you want to. And so the idea is that, let's say, similar to dstream, everything is a data frame. Well, data frame is just a special case of RDD, actually. And every time you apply some kind of transformation, like map, flat map, or filter, or join, I lied to you about flat map. So let's say SQL-like transformation. The result is also a data frame. And so query result is a data frame, intermediate results are data frames, and actually, if you cache the data, it's actually even better because the tables or data frames which you cache will be stored in Spark using columnar compressed representation, so you can actually query them faster. And here is an example in Python, actually. So how many of you know pandas? Right. So generally, Python in Spark is a bit slower than the regular Spark. However, it's not the case with data frames because, well, you do describe your data frame using this API, but in the end, it's still compiled to actual Java bytecode. And so Python doesn't participate in executing this thing, which is nice. And so, well, you can think of it, in the end, it all translates in, you can think of it as SQL, but it's more generic, and you can do different kinds of cool stuff with it. Any data frame questions? So, I think I have time to tell you about columnar table representation. Who knows what's a table, columnar table representation? So the idea is that typically, if you take a regular database, your data is organized in rows, and which is very good if you want to update random rows. So typical transaction processing use case. But if you want to do analytics and you have you want to scan big amounts of data, and you don't want all the columns, but just some of the columns, very often what is used is a columnar representation, where instead of storing data row by row, you actually store it column by the column. And the advantage of this approach is that, well, first, given that each column contains values of the same type, like age or whatever name, it compresses much better. And very often you can use dictionary encoding if you have a fixed limited set of possible values. And it's very good with CPU cache utilization, different kinds of vectorized CPU operations, if you know about them. And also columnar storage can be really nicely represented in Java off-heap storage, so you're not producing this infinite number of Java objects, which is very good for performance. And so there is another trick. What happens is that your table is actually split into chunks. And for each chunk, for each column, you save the maximum and the minimum value. And if you have some filter, you actually don't have to read the chunk if, well, your filter doesn't intersect with the range of your column. And so you can actually skip over very big chunks of your data if you're lucky, basically. And it is used in many data warehouses, like Vertica, Greenplum, and many others. It's also used in many Hadoop analytical formats like Parquet. Yeah, well, here's the list. Redshift uses it, Vertica uses it, Greenplum now uses it, CitusDB, if you know, uses it, and now also Hive uses it. And the nice thing about all this thing is that when Spark, SQL, and DataFrames caches the data, it will also store it in columnar format. So it can be processed much faster, and you can select only the columns that you care about. All right. It is very good for writing if you are just appending, right? So if you have lots of event logs, you just keep writing. Well, it's handled by the underlying format. So the question was how, when writing the files, how do you save them, I guess, the metadata of these chunks? It's handled by the underlying format. You give it a bunch of data, it splits it into chunks, and then, well, you store it. So it's definitely not for OLTP, for transactional processing. This is for analytical processing, like event logs, basically. And so, yeah, there is also a system called Hive, which is a data warehouse which was written on top of MapReduce originally, and was used by many big companies, including Facebook, for, well, analytical processing and log processing. And Spark, I think, made it like 10 times faster, and probably now even more fast, which is pretty nice. So, any questions about data warehouses and columnar representation? Did anybody understand anything? Sometimes. All right. So I'll just dump on you some more keywords, but you don't have to remember them. So we now get to basically analytical libraries on top of Spark. So one is called Spark ML. It used to be called Spark MLlib. So here's a list of algorithms it can do. It can also do pipelines. By pipelines, I mean you can describe your machine learning algorithm in some kind of description. It can be saved, and later it can be loaded. So that's a kind of interface between the data science team and the production team. So data science team has to train the model, and then later it's put in production, and it usually happens in different systems. Yeah, and so lately they also all switched to Spark DataFrames, so it is much more efficient. And it used to be called MLlib, and now it's called Spark ML. Correct me if I'm wrong.
I think it's still called MLlib. I always call it Spark.
The package is called Spark ML, right? The old one is MLlib.
The old one is MLlib, but the library that's actually built, I think, is still MLlib. Yeah. I always, reference it, and the creators of Spark always come in and correct.
I know. So I have to say that, again, Chris can correct me if I'm wrong, that MLlib has some algorithms which are most useful, and probably it's geared towards scalable stuff. Like, probably if you have one big machine and have some specialized problem, you will find a better system for your particular case. Any questions about this library? More keywords. So GraphX is a graph library, and it allows you to implement different algorithms which work with graphs. I hope you all know what are graphs. The important part is that you can represent graphs using vertex RDDs and, more importantly, edge RDDs. And it turns out that for graph algorithms, it really matters how you partition the data, because the graphs which you usually work with, some nodes have way more connections than the others. Like for instance, like some websites have much more links pointing to them. And if you do partitioning of data naively, some of your nodes will be doing much more work than the others. And well, here's a list of algorithms. I'll spare you. I will not read them to you. And now they are also working on a data frame version of all this thing. Finally, we have some pictures. So this is the vision for Spark 2.0. It's not complete, I think. There are some parts which are not implemented yet. But the idea is that everything runs on data frames. Data frames are essentially some kind of, let's say, it's almost like a database query engine. So it has a query planner, an optimizer called Catalyst, and then all this thing is compiled into actual code with binary representation geared towards particular hardware using something called Tungsten. And still at the bottom of all these things, it's Spark Core, which runs on different schedulers. Now, the thing which they are still working on is that something called incrementalization. And this means that you can write a regular SQL query or DataFrames algorithm, and Spark will translate it to a streaming version of the algorithm automatically. So you don't have to have two separate APIs for streaming and batch, but actually you can write the same code and, well, by just telling that I want to have it streaming, it will be compiled into incremental computation, which makes it extremely similar to what Flink does, being patriotic of European Union. And then again, there are the same libraries running on top of all this magic. So these red things are, which are the new things in 2.0, and actually I think not everything has switched to data frames, and definitely not everything has been incrementalized. Any questions about this beautiful picture? Sorry? Because they are not written by the Spark team. These are external systems.
Are they optional, or you have to place all this separate parts? So is Spark standalone, or you need some infrastructure with Java methods?
So you need to run it on some kind of scheduler. So it has its own built-in scheduler, which you can use if you want to, with its pros and cons. And there is also Yarn and Mesos, which are alternatives. So you can basically pick one of the three. Well, for development, not much. For production, yeah, well, it's somewhere. I have two more scary slides. Any more questions about the beautiful picture, which is easy? All right, so again, this is the really scary picture. It just shows you that Spark has become essentially a database engine which runs the queries. So you have a SQL query and a data frame, or a data frame job. And then what happens is that a logical plan is created, which is this execution tree, if you remember SQL, explain SQL, if you have ever done that. Then it creates an optimized version of it using rules, which apparently is very easy to do in Scala. And then it creates a physical plan, which is actually in terms of actual operations on data, and probably also considering the binary representation of the data. And it generates a bunch of them and then estimates their cost and picks the one which it thinks is the most optimal. The thing is, of course, that for cost-based optimization, you need to have good statistics about your data. So if you don't have good statistics about your data, your cost-based optimization will not be very good. So I'm not sure how far they are with this part. But in the end, you get a physical plan. It's compiled into RDDs and a bunch of custom generated bytecode, and then magic happens. And apparently, if you're lucky, it uses CPU caches and vectorization instructions and all the magic. And final slide with scary pictures, or words actually in this case. So structured streaming is something which is in alpha. Yeah, question.
On the previous slide, does it collect statistics automatically?
As far as I know, not.
But how do we then get them to green plans?
They don't do it much yet, as far as I know. So yeah, and then the new cool thing is that Sparse Streaming can be replaced by the regular data frames, which can be automatically incrementalized by the query planner. So you get essentially the same API for batch and streaming, and you just tell, please run it incrementally on this Kafka stream. I had to put it here, prefix consistency. So what it means is that at each given time, the output of your streaming job will be a function of some prefix of your Kafka stream. So it will, anybody understand? At every moment, the output of your Spark streaming job will be a function of a prefix of your incoming event stream. Go computer science. And finally, yeah, if your output thing is transactional, then it will produce essentially a snapshot of your output RDD into the external data sink, which is consistent. And it can write to databases, key value stores, and so on. And yeah, I have some more scary and less scary slides, but basically that's it. So if you're still not sleeping, ask me questions or Chris. No. Yes, depending on the use case. So we're kind of hovering between this small and big data, and it's not clear yet that it pays off for us.
What will be the kind of crucial moment when you will actually decide, we need to go to the Spark and the big data rather than the current solution?
So
I don't believe that you will just, okay, like now we have 100 computers, we need to implement this. I don't believe.
Yeah, sure. So I think many people get away with just Akka, maybe Akka persistence. That's what we do so far. And you know, it's in the end engineering decision because you have some investment in your existing code base and so on. But you know, if you're a unicorn and you have too much data, then probably you can afford Spark or something similar. It also depends, like if you have very specific use cases, like you have analysts running SQL queries, maybe Redshift is a better solution for you. So if you're trying to do some machine learning or something custom, then or some complex ETL pipelines, extract, transform, load, then it might make sense for you. Maybe Chris wants to.
Yeah, the first I ever really experienced the big data thing was when I left Chicago and moved to California, and I joined joined Netflix, and that was the first time I experienced where I couldn't run a job fast enough. You know, it was taking 3, 4, 5 hours to get answers, things that in Chicago, like relative to the types of data I was dealing with there. Which was a lot of financial, type stuff, but not really media apps where they were tracking everything, right? They were tracking each, play, each stop, each, fast forward, like rewind, all that. And it was the first time I'd seen where we were deploying, 5,000 servers, right? Like normally we would have one big ass server with, 32 cores or something like that, but it was the first time where I saw many, many servers that were all logging, right? Like the big joke about Netflix. I think you guys have like Netflix here now, right? Is it just the recent one? Was it just recently? About 6 months.
It has less selection, definitely.
Yeah. Yeah, well, so one of the reasons Netflix continues to claim that they make money, I don't really know if they do actually. I guess, like someone knows, but it didn't seem like they were making money when I was there. They would spend a lot of money. And still charge you guys, $7.99 or whatever it is because of the recommendation engine. So they don't pay for the first run movies, but they'll convince you that you'll like some shitty movie, right? And you'll be just happy enough that you'll continue to pay. So, but
and like the big joke is that Netflix is a logging company primarily, right? Like server logs, and then secondarily they actually stream movies, which is like feeds into the whole thing about not like making money. So they push all the logs through Kafka. They end up in S3. Application teams can tap into the Kafka stream if they want sort of near real-time access. For things like multi-arm bandit, testing, things like that. What else? Yeah, I mean, yes, I worked at Databricks, which is the company behind Spark, and at the booth all the time people would ask about, or like Redshift, why do we need Spark? And that was a tough one to answer. I mean, I was forced to say, yeah, you need to have Spark. Yeah, one really interesting use case, I actually was just talking to one of my old like Netflix buddies who went to Quora, yeah, I can't say that word. And the engineering team he took over was like super Spark heavy. I think that they were training, they were doing matrix factorization for the recommendations on a 15-node huge Spark cluster. And it was taking, 5-6 hours to run because of all the shuffle and the data, going between all the distributed nodes. And so coming from Netflix, he was pretty comfortable with that. But one thing he couldn't do at Netflix was tell people not to use distributed systems because, as like developers, that's the holy grail for us, right? Is to work on distributed systems. So single node stuff is boring. He basically allocated one developer to rewrite on one single node in C++, and on the same data set, which was a huge data set, took, I think, 14 minutes, yes, as opposed to the 6 hours of, so that's an example where if you just kind of step back and, there's still lots of people using R, on a single node. I think the Databricks guys and the Spark community is trying to force R down, Spark R, down people's throats, but it's not necessarily the best way to do it. So, I mean, the techniques are all still there where you sample and and then really do your really testing and validation locally on a single node, and then you can push it out to the cluster. But the big data thing, I mean, there's very, very few companies I see that actually have big data. It was single node, and the way it was still parallelized. It was using all the cores. I think it was an 8-core machine. But the reason it was taking so long on the Spark side is that like parallelization was happening across like the network, right? So all the data had to transfer across. So it was still a pretty beefy machine, like it had a lot of RAM and everything, but not all the RAM, like data fits into RAM with this algorithm. In fact, I think they actually open sourced it. It's called QMF, Quora Matrix Factorization. It's written in C++, which I know I'm starting to get my C on again, feeling good about it.
I think there are also lots of specialized systems. Like if you have a graph processing problem or just string processing problem, there are specialized systems which do it better still. And I think Spark has gotten much better, right? So compared to, let's say, Hadoop, like orders of magnitude. Memory usage, CPU, cache allocation, vectorization. But there is still room for improvement, especially if you're a specialized system, you can always write a specialized code.
Yeah, that's the thing is that like they knew that specific workload and can make the optimizations needed. There's a lot of people that have submitted updated like matrix factorization algorithms for Spark even that just don't get picked up by the Spark core or the Spark ML project. But is there anything I was going to say? Yeah, I mean I think like Redshift like does a pretty good job. Like one thing with Redshift, not sure if you guys know about it, but there's like the approximate keyword, right, that you can put in front, which switches over to hyperlog mode. So that's something that you guys want to look out for. If you're doing a lot of SQL and don't really need the exact count, right, if you're not counting pennies at a bank or whatever, if you just want to look at the number of errors, that was a common use case for us. At like Netflix, we would do releases at the time. This is about 3 or 4 years ago. We did them every 2 weeks, and after the release, I just wanted to know, or like relative to the 15 minutes before, right? Like, did certain errors go up? And at the time, because we were using Hive, which generates MapReduce under the covers, and I think the actual data pipeline itself was not Kafka-based, and so it would take about an hour for the data from the servers to get to a point where I can run the Hive query, which then took 2 hours or whatever. So, but right, like the ability to just run an approximation. So yeah, something like Redshift, which works pretty well too if you have if you have your data going into something like Kinesis. It's just a point and a click away to send it into Redshift and all that. It's not my jam. I don't like pointing and clicking at my architecture, but yeah, if you want to, like you can get pretty far. So, but yeah, check out the approximate keyword, and I think it's less than 1% error, and it comes back within like minutes instead of hours.
But Spark has BlinkDB, which doesn't.
BlinkDB. Yeah. So actually, do you know? Yeah. So I'm curious. Does anyone know about BlinkDB or like heard about this thing? Is that Vilu, by the way? Is that you, Vilu? Yeah, there's probably like 20 Vilus here. Okay. Yeah, so I'm looking for this guy Vilu that I
maybe we should tell people what it is.
What? Oh,
BlinkDB.
Oh, the BlinkDB. Yeah, I tend to get sidetracked. BlinkDB is like a probabilistic like way to query into Spark. So like stop thinking about queries as like an exact answer and start thinking more in terms of time-based timeouts, right? Like I want an answer within a minute, or like an error bounds, right? Like error confidence bounds. So, but yeah, so BlinkDB, the person that created it now works for Databricks, and those key concepts are in Spark. It's just which is why the actual project BlinkDB itself seems to have not been touched in a couple years, but really it's part of. Yeah, so with Spark, there's ways to do like approximate counts and things like that are on the DataFrame API and the RDDs. Yeah.
And approximate joins?
That's a good question. Approximate aggregations, I don't know. And joins, I don't think so.
Not yet, I guess.
The package is called partial. It's org.apache.spark.partial, and it's essentially doing as much as it can inside of the time that you're giving it, and then just returning partial results. So I'm wondering if the join, if they can even optimize that. Yeah.
So Facebook used to use lots of Hive and Presto, right?
Yeah. Facebook still uses Presto pretty heavily. Yeah.
At some point, they were considering this commercial database starting with letter V.
Oh, yeah, Vertica?
Yes.
Were they?
Yeah, I think so. That's a rumor. I don't know.
Back in the day? Yeah.
It didn't happen, or?
I don't know. I don't know anyone over there using Vertica, but yeah.
Okay.
Yeah, I'd never heard of that before. Mm-hmm.
So what should we use for streaming?
For streaming. Yeah, so this is on the eve of the Spark Summit, so we should probably talk about Spark. But Spark is starting to become known as just an ETL tool, just like a faster, Hadoop, which is shocking to people. Like people don't really want to think of it that way, especially Databricks. But the streaming stuff has kind of fallen flat. Hopefully, right now they're sort of planning, right? Like Matei and those guys, the main creators, are planning to re-architect streaming to make it more like Storm, right? Like a per record.
Or Flink.
Or Flink, right. Yeah, they don't use the F word around the office. So Spark Streaming in its current form has a lot of limitations and might not be what you think of as typical streaming, like Storm-based streaming, and like complex event processing. But what should you use? Yeah. There's a project, so Twitter just rebuilt Storm, but like preserve the core Storm API because they have so many Storm topologies or jobs or whatever. And it's called Heron, Heron. Yeah, so that's it. I don't know like anyone beyond probably Twitter that's actually using it, but they finally open sourced it, and that seems pretty promising. There's this other spec that it's called Beam, right? Like the Apache Beam project. Yes, anyone heard about this? at the recent Strata conference out in New York, there were like 5 talks. These guys from Google are starting to come out of their shells or whatever. Yeah, I don't know.
So Beam is like a SDK, right? It
Yeah.
still compiles to either Spark, Flink, or
got
Google's
different-
Dataflow, right?
Yeah, exactly. And so what's happening here, this is the same thing happening with TensorFlow, with Kubernetes, and with Beam, is that Google, right, yeah, so because they're so far behind on like the whole cloud thing, right, like Amazon is just like eating them up, they're trying to push out, right, like more of these implementations, right, like rather than just throwing over the wall like a white paper, right, like they did with MapReduce. And that, the thinking there is if you can get enough people to buy in to not just the spec, but not have to rebuild an implementation like Hadoop, which was built at Yahoo, that they have more control over how it's gonna like evolve throughout the years and stuff. So people, and then like of course, if you start using these things, TensorFlow, and you want the best performance, you would go to the source, which would be Google and the Google Cloud. So.
And TPUs?
Oh yeah, the was it Tensor Processing Unit or TensorFlow Processing Unit? Yeah, it's supposed to be a replacement for the GPUs.
For serving mode, right? Not for learning.
I always thought the TPUs were meant to be on the mobile device because they were really low power, but I found out later that low power, it's still relative to the server, to the current GPUs running in the data center. So I've heard it used for both,
Cool.
but they're a little bit wonky on that. Yeah.
Last question, and then the beers and pizza are cold enough, we can start consuming them. So what do you think of Kafka streams?
Yeah. Oh, yeah. So actually, I didn't mention that. Kafka streams, if you aren't currently tied to anything Spark specific, or if you can kind of work around Spark a little bit, right, like by maybe using your own machine learning algorithm or even just taking Sparks. And I like Kafka streams, like especially because most people, and it sounds like here too, there's a lot of people using Kafka. So if you can, it's very difficult to reason between 2 distributed. It's like hard enough to reason within one distributed system, but now you go from a Spark cluster or from a Kafka cluster down into Spark streaming. So trying to reason across those boundaries is difficult. So if you can write your jobs directly in Kafka streams, you still get parallelism. You still get like the ability to like join streams with like static data and things like that. But most people are a bit, and same with Flink too. Like they don't want to learn this new API, right? They've got everything running in Spark right now.
So I guess Spark is more like a Lambda architecture, right? So the fast layer and the batch layer are separate and then merged together in the serving layer.
Yeah. Spark doesn't really have a serving layer, I guess.
Sure, but the idea is that you take them as 2 pieces, right? Streaming piece, batch piece, and you get a Lambda architecture by putting something else in the end. Right?
Right. Yeah, in fact, that's one of the demos I'm going to try to show today is building the serving layer, which would be like the prediction layer, for the machine learning algorithms. Right, like most attempts at that these days, people are trying to make Spark act like an application server, which it's not meant to be, right? It's not like multiplexing, connections, and every connection that comes in is a Spark job essentially, and it takes up at least 1 CPU, and it scales. It's just very expensive to scale, right? It's on the per CPU. So if you have 1,000 concurrent users, you have to have 1,000 cores, which isn't very good. So I'll show a way to use Netflix open source and then building microservices, and then we can train the model and then push it out into the live running cluster, and then show.
Cool. Yeah. So Kafka Streams is advocating this Kappa architecture, right?
Yeah.
Is it based on Kafka or JKreps?
Yeah. The whole Kappa architecture is kind of a mockery of the Lambda.
But their idea is that you don't have 2 separate layers, right? You have one very fast layer.
Right. Yeah, so, and then because now with, I think the newer versions of Kafka, there's something called a compacted topic, which is constant, it's not that new of a concept, I guess, but it's constantly materializing, which is basically like a database, right? But the thinking is that you could also go back and then replay, and you're just like executing really just like any other transaction log, where the inserts, the updates, the deletes, things like that.
So if you had to build a new system for something, you had to pick between Kappa and
Man, I've
Lambda.
talked to so many people about this, about treating all data coming in as a stream and logs, and people are freaked out. No one can grok this, and it's tough for me too. I mean, I'm kind of old school in my data thinking, but
I guess it's a trade-off a bit.
Yeah.
Like it's harder to debug, but if you get it right, it's maybe easier to
yeah.
write.
I mean, it depends on the use cases, and you really have to know Kafka pretty well, I think, at that point, and have to keep, because essentially, like, you're either going to keep, something I'm seeing now too is people have multiple topics or queues with Kafka. They have the first one coming in that's like maintaining everything, and they just have to keep growing disk and disk and disk. And then they ship that to another topic, which is then the compacted, like materialized topic. And then the application teams can choose which one that they want to pull from. But
Cool. Now I think we got people really hungry.
yeah.
So let's have a half an hour break.